Welcome back to the lecture series on fundamentals of air pollution. We will continue in this lecture again with the aerosol optical properties. In the previous lecture, we discussed about the processes like absorption and scattering, and we derived the concept of absorption coefficient and mass absorption efficiencies, and we discussed their importance. And at the same time, we related this that some of the absorption and scattering coefficient is called extinction coefficient, and this extinction coefficient is very important for daily life. One of the things is like haze and visibility. So, we will see some of the case studies in this lecture, and we also calculated that how you can calculate the scattering coefficients based on the aerosol composition. If you have given the aerosol composition, you can use the literature values that is available for mass scattering efficiency and absorption efficiencies, and you can just do this one. So, I hope that this is the point I discussed in the previous lecture, that you have a extinction because of the different species, and each species has a kind of mass scattering efficiency, and using these equations, if you know the mass of the particles, for example, if you have just measurement of aerosol chemical compositions and you just use these values that is actually published in the literature, and then literature you can get the values from the literature, and then you can calculate V extinction here, and this is usually called reconstructed extinction. And I discussed about the importance of relative humidity here, and this I also discussed that this ammonium sulfate and nitrate, they will not exist as ions, separate ions, until and unless you measure them, dissolve them in water. They will be actually in the form of their salt, respective salts, and these are the very important salts that are there. And the another important component is actually like carbonaceous aerosols that we discussed in the previous lectures. We have so much about that, like elemental carbon or black carbon, and then organic carbon. So, this is because of these you can calculate the extinction efficiencies, and some of the coarse matter, which is basically you can talk about the larger particle, that is dust. So, you can calculate the extinction. Now, once you have calculated the extinction, this extinction is directly related with the visibility, and we will see how. So, as we discussed that scattering cross section, just remember again, it is the same as mass scattering efficiency is the product of mass loading and the surface area per unit, or sorry, this is again just I am also confused here. So, this is a scattering cross section is not, this is actually scattering efficiency, scattering coefficient, okay, and this is said that is the mass product of the mass loading. So, you have sum of the concentration, and then you have surface area per unit mass, which is called mass scattering efficiencies, okay. So, you just do this one and you calculate, and if you do this calculation, ln of 0.02, if you just do, this is the actually the maximum visibility that we will see, we call about. And when we talk about this is ln of means what we see, we had the equation I is equals to I0 into exponential minus B extinction into x, say. So, if you see this one I upon I0, and then you take log of this one is equals to minus B extinction into x, and this is the maximum limit, okay, that ln I0 only 0.02% of the radiation is actually you can see that most of the radiation is transmitted. So, what you have this value, you have ln I0 upon I, this is I upon I0 is 0.02, and you take log of this one. This log of this one is actually minus 3.9, and if you just put this value, minus 3.9 will be equals to minus B extinction into x, and from here you can actually calculate x, that how far you can see is actually nothing but 3.9 upon V extinction. So this is the value. This is the actually equation that we usually use for calculation of the visibility if you know the extinction coefficient. So as you can see, x is here actually like visibility. So if you have higher V extinction, means more attenuation of the light, then this means this is actually constant. So this is visibility is inversely proportional. So you will have a smaller visibility, very low visibility, and if you have extinction values that is very low, then you have very high scattering, and this is very practical. Extinction, high extinction means more number of particles that are there in the atmosphere. So this means if that high kind of high polluted atmosphere. So when you have high polluted atmosphere, the visibility becomes very low. So this is actually we discussed in this one, and I also discussed in the for example the mass scattering efficiency. For example, here is given for the sulfate particles about 3.2 meter square per gram, where humidity is less than 70%. So if the humidity is more than 70%, this value will change, actually this will increase, but for the values RS value is less than 70%, V extinction due to sulfate particles can be taken as 3.2. And thus if you have mostly sulfate particles, then you can just see this one. Okay, there is something actually wrong. This is actually sigma extinction, the unit is wrongly written. This is meter inverse. Okay, so 3.2 meter, and if you just put meter inverse here, then the visibility will be this will be meter inverse, this will be meter inverse, so about 1.2 meter. This is just because of the sulfate particles, single sulfate particles, but when the atmosphere you don't have single, you have many number of particles. So this is you can actually calculate the kind of extinction that is there. So sometimes researchers relate visibility to the scattering coefficient. There is actually confusion of that visibility is whether related to the scattering coefficient or extinction coefficient. Remember, scattering is actually just that particles is getting scattered. Absorption component is not considered, but when the light attenuation happens, light attenuation can happen because of the scattering as well as absorption. So you have to consider the absorption here, the absorption as well, attenuation due to absorption, and because of this reason this should be used as an extinction coefficient. This is example that is given. This is actually for the case of 2003 North American blackout. This visibility improvement, that how they discuss. So during the normal conditions, you have scattering V I just I put this is actually V scattered. Okay, that is actually 120 mm inverse. Remember, mm inverse means 10 to the power minus 6 meter inverse. And if you also remember that I talked about that this is usually is between 10 to 1000 mm inverse, these values. So you can see that the values are actually 120, slightly higher. Okay, during the air pollution episode. So when you had a air pollution episode, the V extinction scattering was relatively higher, and this can be written as actually as I said that. So if you write here 120 into 10 to the power minus 6, then it will be 1.2 into 10 to the power minus 4 meter inverse, and then you see values 550 nanometer. This is wavelength is very important. Whenever we are reporting the scattering and absorption coefficients, we must report the values at what wavelength we have measured. So reporting the wavelength is very important. You see here absorption is very small. So 0.8 into 10 to the power minus 5 meter inverse, and if you just add this one, this is so you can write this number will be actually like 120 into 10 to the power this value is something wrong here actually. Yeah, no, it's correct. So this will be actually 0.08 into 10 to the power minus 4. So this value will be 0.08 into 10 to the power minus 4 meter inverse. Why I am trying to say this 10 to the power minus 4 I have here, so I have to use the 10 to the power minus 4, then only I can put. So then V extinction will be 1.2 plus 0.08 and 10 to the power minus 4. This will be meter inverse. This will be actually like extinction. So what will be the visual range? You can just put these values 3.9 divided by 1.28 into 10 to the power minus 4 meter. Okay, and 12×36 about 3 and into 10 to the power 4 meter. This means about 30 kilometers. So the visibility during the normal condition is like 30 kilometers. During blackout days the scattering coefficient is less. Okay, the scattering coefficient is 40 into 10 to the power 40 million inverse million meter inverse, and V absorption is 1.2 into 10 to the power minus 5. So you can calculate the V. Similarly, it will be V extinction will be 0.52 into 10 to the power minus 4, and then this means you just put this value here, you will be able to calculate that what is the visual range that you can calculate. That is actually 75 kilometers. This is practically not possible. This is practically very high values, but this is sort of theoretical considerations that we have, but actually it is possible to just give some idea that actually that visibility can be related to the this one, the scattering coefficient and absorption coefficient or extinction coefficient. So in the optical instruments, how do we measure scattering? So this is I said that nephelometer. I talked about these instruments. This measures total scatter and hemispheric back scatter. This is very important. So it measures, and it uses a known source of light, known path length, and obtain scattering coefficient. So usually you get V scat. Okay. Now we have V scattering. You need to have V absorption as well, and V absorption is used either by particle soot absorption photometer or several times we use athalometer. Okay. This is another very important optical methods, and this was very commonly used. This become famous in very recently, and this can be used actually to calculate your absorption coefficient. So from here what you get V absorption. Okay, and this measures absorptions through the filter paper, and this provides absorption coefficients. So when you have these two values, you can just add V absorption and V scattering plus V absorption. This will give you V extinction. So this value you can get it actually. So this is very important concept about the in situ measurement of this one, and then of course as I said that combination of that two will give rise to the extinction coefficient. Then another very important parameter about the optical properties is single scattering albedo, and as I just remember this one, what was the albedo that we are defined? Albedo, what was the light that is reflected back divided by the total. Okay, and for example for the earth we discussed that earth albedo is about 0.3. So about 30% of the radiation is reflected back to the atmosphere, and only 70% that is actually coming. 30% is reflected back by the clouds and aerosol particles and other stuffs like you have, and then 19% is absorbed in the so you have like albedo is actually like 30%. So 30% is reflected back, 19% is absorbed by the atmosphere. So this means you have like 49%, and remaining 51% that comes to the earth surface, which is actually absorbed by the and then reflected. So similarly, in the aerosols we define single scattering albedo, and it's like to similar one. This is actually, this ratio is a measure of fraction of aerosol extinction caused by the scattering. This is very important. So what means, you can write actually, or you can write omega 0 is like, omega is, you can write V scat divided by V scat plus V absorption. Now consider the two situations when V absorptions is nearly 0. What will happen? In this case omega will be very close to 1, because then you don't have any component of here, you have mostly scattering type of aerosols, and this is the condition when you don't have we don't have black carbon species like in the atmosphere. And in some of, so this means this one, and other case you can consider when the V scat is actually 0, there is no scattering by the particles, and this case omega will be 0 because the scattering becomes 0, you still have some particles but omega will be 0. So omega values lies between 0 to 1, it will be more than 0 and it will be less than or equals to 1. Remember this one, this higher values, when the values are higher, this means when the values are higher, when you have less absorption. So this is actually less absorption, and this means you have more scattering, and this is actually, so this means it's dominated by more scattering aerosols. So that time the atmosphere is dominated by most scattering type of aerosols, and if you have values closer, lower values, then you have more absorption, and this means more absorbing species. And when they are there, they will be absorbing and then they will be re-radiating in the atmosphere. So you have warming of the atmosphere, and in this case you will have cooling. So you just remember now, by just looking at the concentration of scattering and absorbing aerosols, you cannot tell that whether there will be a warming or cooling. What we have to derive, but if you have known the values of single scattering albedo, then it is a better predictor for the kind of warming or aerosol absorption, warming or scattering. This is actually we have already discussed, so let us not discuss again here. I just give the example. In the previous example, if you remember, we calculated, during the pollution days, our B extinction was about 1.28 into 10 to the power minus 4, and this was about 0.08 into 10 to the power minus 4. So you can just calculate. Okay, so you had actually like so you had 1.2 which is scattering, and this was 1.2 plus 0.08, and of course there was actually 10 to the power minus 4, but it will be in the both in the numerator and denominator. So this will be cancelled out, and we will be left with 1.2 divided 1.28, which is actually 0.94. Remember, there was actually something wrong I wrote in the previous one, so just let me correct here. This is actually is not the, this is actually pollution condition. It's correct, it is during the air pollution episode and during the blackout. It's correct, okay, no problem. And during the blackout, what is there? You had 0.4 and 0.52. Okay, you just remember this one, this is very important. So the omega values becomes 0.77 and here. So this is actually dominance of scattering type of aerosols, and this is dominance of absorbing type aerosols. Okay, so just remember these things. You can just see this paper that we discussed actually. And there is a very important question to ask. As I said, that this is actually kind of, this tells that whether the atmosphere will be absorbing or the kind of scattering one. So you see here, as I said, that critical scattering albedo, the critical single scattering albedo will be varying from 0.0 to 1. Okay, you have kind of different scenarios that are given, and if the values are here, in this one values are dominant, and then this is the actually surface reflectance values. So if the values are here, you have a negative forcing. So this means here you will have a kind of cooling, and this means you have this. If you just take these values, what is there actually? The most of the time you have values that is higher. So omega is larger. So this means omega is larger, means you will have cooling dominated by the scattering aerosols. Here you have mostly values that is actually lower. For example, this region. So here the actually forcing will be positive. So this means you have warming in the atmosphere. Okay, yeah. Then there is actually another very important parameters, but I am not going to discuss that one in details. This is optical properties of smaller particles. Is if you just see refraction or refractive index. So refractive index can be written as complex number, m is equals to n plus ik, okay, and n is actually for the scattering part, okay, and k represent which is imaginary part, which is mostly for the absorption. Okay, so the real part of the index refraction is only weak function of wavelength, while the imaginary part depends strongly on the wavelength. And this is also very important. When k is more than 0, this is actually this part. When this part is actually negative, you have warming or kind of absorbing. So for most of the absorbing aerosols, you have negative imaginary coefficients. Yeah, so this is aerosol optical depth. I discussed this equation, and then one more thing is here actually I discussed this about the Beer-Lambert's law for gaseous species. You can calculate sigma n into s, and this value is given by the tau. So this is actually optical depth because of the uniform distribution of the gas in the atmosphere. Similarly, you can calculate the in that case it will be actually B extinction into x. This is actually for the aerosol particles, and then this, if you integrate this one, you will get the tau, and this is actually called as aerosol optical depth. Another thing is actually like aerosol optical depth. If you just calculate this one, so the radiation that is coming, if you just take a small angle, if you just say solid solar zenith angle, SZA, solar zenith angle, so what will happen? And if you just calculate this thickness actually dz, but when the sun radiation is coming from this direction, this ds will be actually dz upon cos of this number. So you can just calculate, put it here. Okay, you have a kind of right. So you imagine this one actually. So this is length, this is perpendicular, and this is actually this is the base. Then you have a perpendicular, and then hypotenuse. So ds, this one hypotenuse, you can cos theta is written as actually perpendicular divided by the base upon perpendicular. I just remember this one, so that you can remember, and you can just see this ds can be written as dz upon cos ZA, and then this means I0 upon I I upon I0 can be written as sigma n sec of Za and dz. So, you can calculate, this is actually schematic radiation, and that is what happens when the sun is not on the top. It is actually during the horizontal period, then you have more scattering of the particles, because the value becomes more. You have to, it encounters more particles. You can just visually see here. If it is falling in this one, then it has this one, but when it is falling this, it encounters more number of particles. So, that is how it is done. Another important parameter is from that tau is actually wavelength dependence, that is lambda to the power minus 1. So, if you want to calculate tau at lambda divided by tau at lambda 0, this will be lambda upon lambda 0 to the power minus alpha. This equation is very important, and this alpha is called angstrom exponent, and angstrom exponent is actually a measure of size number distribution. So, typically if you have a larger particles, okay, this is larger alpha means fine particles, like you have mostly in the urban areas, and when you have smaller alpha, you have coarse particle, and this is like kind of dust storm condition. So, people have studied and they have done the characterization of aerosols, that how they can be actually represented, how and what kind of parameters can be there. So, based on the alpha values you can calculate this. So, with this one I stop here, and I thank you again for your patience listening, and I hope you are enjoying and you are reading and understanding the concept of optical properties. I think at this point we will stop on the optical properties. In the few sections we will come discuss aerosol cloud interaction, aerosol radiative forcing, or impact of aerosols, and then if there is a time we will just introduce some of the statistical parameters that are there. So, with this I stop here. Thank you very much.